All right, the next one we're going to do is number 49. 49 says, a gray kangaroo can bound across level ground with each jump carrying it 10 meters from the takeoff point. Typically, the kangaroo leaves the ground at a 20-degree angle. All right, so we're doing a kangaroo here. So here's our kangaroo. His big legs. That is the terrible kangaroo. But it hops, and it can hop 10 meters. All right? And it launches at an angle of 20 degrees. What we want to determine is what is its takeoff speed and what is its maximum height above the ground. So we got two things to get. A, we have to figure out V naught, and B, we want the max height, or H. And the max height is going to occur somewhere here, right? It's going to occur in the middle of this parabola. So let's do part A. Well, we have an advantage here. We know that it lands and takes off at exactly the same height. So if we do that, oh, if I put a tail back here too, right? That is the ugliest kangaroo you've ever seen. All right. We know if it launches and lands at the same height, we can use our range equation. The range equation says V naught squared over G is sine of 2 theta. Theta. And so, remember this is 2 theta like this. You don't do sine of 2 and then it's like theta. It's 2 theta and then in the sine. We want to solve this for V naught squared. So we're going to take R times G divided by sine of 2 theta is equal to V naught squared, or V naught is equal to the square root of RG over sine of 2 theta. Hey, we have all those numbers, so this is actually very easy. So V naught is just going to be the square root of the range is 10 meters times 9.8 over the sine of 2 times 20. When you do that, you get that its initial velocity is 12 meters per second. So that's the answer to part A. Now part B, we need the maximum height. So what we need to do is figure out when it's at its maximum height. And so to do that, we're going to take advantage of the fact that, well, when it's at its maximum height, Vy is equal to 0. So remember, we're going to use this equation. So I'm going to use this equation right here. Vy is equal to V0y minus gt. We now know what V0 is, and remember, V0y is equal to V0 times the sine of the launch angle, and V0x is V0 times the cosine. So I'm going to plug that in for V0y. This is going to be 0 at the top here. Remember, Vy is equal to 0 here. So this is going to be 0 is equal to V naught sine of theta minus gt. And I'm just going to solve that for t. So I'm going to put this on this side and say, oh, gt is V naught sine theta, or t is equal to V naught sine theta over g. And so you can figure out the time. We have 12 times the sine of 20 all over 9.8. And you calculate that. You grab my calculator here. And I find that we get a value of, let's see, 12 times the sine of 20. Always make sure your calculator's in degrees as well. You start getting weird answers, that's usually the first thing to look at. And we get a time of 0.4188 seconds. Notice I'm not rounding it off because I don't want to mess up my answer. So now I say, okay, what I'm trying to find is the maximum height. I know the time, so I can just plug it into this equation because I'm trying to solve for y, height. So y is going to be equal to y naught plus v naught yt minus 1/2 gt squared. Well, y naught is 0. The initial velocity in the y direction is going to be v naught sine theta. So we're going to put that in there. So we've got v naught sine theta times t minus 1/2 gt squared. So I just plug all that in. And I'm going to get y is equal to v naught we have is 12 sine of 20. All that times t, which is 0.4188, minus 1/2 of 9.8 times 0.4188 squared. And when you do that, you get the maximum height is 0.91 meters. All right. By the way, this is very impressive. Remember, 10 meters is 30-some feet. That's what, like, Olympic long jumpers are in the range of, is leaping about that. So kangaroos can do that continuously. So they have a very powerful launch, and they can really launch far. In fact, they're very efficient at going very fast launching. The problem with being bipedal like they are and hopping everywhere is it's not very good, not very efficient for doing short, slow motion. It's great for doing long, very fast motion. That's the answer. This is part B. Answer to part A and B, that was number 49.